Okay. Thank you. We have the pleasure here today of having Dr. Seunghee Park with us to give a talk on some of his research in structural health monitoring. Dr. Park is currently an assistant professor in the Civil and Environmental Engineering Department at Seunghee Kwan University, not too bad, in South Korea. Dr. Park got his bachelor's, master's, and PhD all at KAIST, which used to be called the Korean Advanced Institute for Science and Technology, but I understand they've just changed it to KAIST. It no longer is an abbreviation. Anyway, so he worked with Professor Yun at KAIST, which several of us know, and then spent about 1.5 years at Virginia Tech working with Dan Inman as a postdoc. So thank you, Dr. Park, for being here. We look forward to hearing your seminar. Thanks.
Thank you. Okay, thank you for a nice introduction about me, Dr. Johnson. Again, my name is Seunghee Park. I'm an assistant professor at the Department of Civil and Environmental Engineering. Also, I'm working at Department of UCT Design and Engineering at Seunghee University in Korea. Today, I'll be talking about ubiquitous sensing-based structuralized monitoring and energy harvesting. Okay, before I start my presentation today, I will just want to briefly introduce about myself. My professional interest is based on smart sensors and structures, especially health monitoring and vibration control issues. These days, I'm working for radio frequency identification, wireless sensor node, and sensing network technique. And basically, I'm interested in information data mining, signal processing, and static pattern recognition issues. My background is civil engineering, so I've been working about structural dynamics, random vibration, and earthquake engineering as well. Okay. These are a list of my professional experience and education background. As Dr. Johnson already talked, I got bachelor, master, and PhD degree from KAIST in Korea. I have several experience about visiting scholar, adjunct researcher, postdoctoral researcher, and being professor at Virginia Tech and KAIST as well. Okay, this is my presentation outline. Firstly, I'm going to talk about ubiquitous sensor network system, and then briefly talk about U-safety infrastructure. We call it smart structures. Then I'm focusing on the piezoelectric sensing-based structuralized monitoring and energy harvesting issues toward to multifunctional wireless sensors, including structural damage detection and sensor self-diagnosis and energy harvesting issues. Then I'm going to conclude my presentation. Okay, first I'm going to talk about ubiquitous sensor network. These days we are living in a ubiquitous society. We experience a lot of sensor network system, even though we are using cell phone and other network system, we don't recognize that event. As you can see here, we call it smart dust that consists of embedded system, MEMS, and networking system. By using this kind of USN, we can think about a lot of USN convergence industries, including supply chain, automotive, environmental monitoring, digital home, building automation, automatic meter reading, and others. These days, we can use a lot of UVconsensual applications, as you can see here. And from the evolution of USN technology, today I'm going to talk about smart structure technology and energy harvesting issues. Okay, first item is the structuralized monitoring. As you can see here, we have experienced a lot of collapse accidents at civil infrastructures. To prevent those kind of collapse accidents in advance, we need to develop more reliable and more economic structuralized monitoring technique. As you can see here, we need to develop youth safety infrastructures. We call it smart structures. Buildings, bridges, and other civil infrastructures, they might have their own brain and optimal sensory systems. If urgent event, including typhoon or earthquake occurs, we need to estimate health condition over target structures, and optimal sensory systems can be measured some damage sensor features. Then diagnostic results are transmitted to the data management server throughout the sensor network system. So we need to develop smart structures to prevent some collapse accident under emergency situation. Our final goal is to develop smart structures. As you can see here, we can see some functions of smart structures. Do you know who she is? She's a figure skating player in Korea. Her name is Yeona Kim. I hope she win the gold medal of, Vancouver Winter Olympic next month. Anyhow, we want to develop a smart structure like our human body system. Actually, she has very smart and intelligent body system in terms of not only appearance but also functionality. As you can see here, sensor system such as eyes and nerves, and control system such as control system like balancing organ and other biological system. So we can improve the safety and life cycle effectiveness of civil infrastructure for ubiquitous city construction. What you see here is a schema diagram of bridge-based monitoring control systems. You can see a lot of kinds of smart sensor systems, including piezoelectric sensors, accelerometer, GPS sensors, and fiber optic sensors, and other kinds of damper system for vibration control. One of them, I'm gonna talk about piezoelectric sensors today. As you can see here, piezoelectric sensors have a unique molecular property. We call it piezoelectricity. Piezoelectric effect couples mechanical strain to an electric field, allowing for both sensing action and functions. This is by constant equation, as you can see here. So these are strain term and stress term. So this is for general material, but piezoelectric material has another electrical term into as you can see here. So they have coupling effect between mechanical field and electrical field. That's why we can use piezoelectric materials as both sensor and actuator at the same time. By using this material, we can convert mechanical energy into electrical energy and the other way. There are a lot of piezoelectric sensor system already commercialized, as you can see here. This is a ceramic and this is polyvinyl materials and paint material and composite materials. By using piezoelectric sensors, we can employ active sensing based SHM technique into our civil infrastructures. There are two kinds of active sensing SHM technique. One is electromechanical impedance method. The other one is guide wave propagation method. As for the electromechanical impedance method, we can put PGT sensor to the whole structure. Then we can excite the whole structure by using PGT sensor in a high frequency excitation. Simultaneously, we can obtain the frequency response function from the structure. So as you can see here, if a damage occurs in the structure, the real part of impedance signature will be changed due to structure damage. So by monitoring some change of impedance signature, we can monitor health condition of structure, whole structure. The other way, as for the guide wave propagation method, as you can see here, we can guide some elastic wave, such as Lam wave or Rayleigh wave propagation into a structure. Then if some damage occurs on the wave path, some wave mode reflected or some scatter occur here, so we can detect some structure damage on the wave path by using wave attenuation or mode conversion effect due to damage. Okay, this is one example using impedance-based SHM technique for pipeline system monitoring. We can detect some loosen bolt damage into the pipeline system by monitoring some changes into impedance data in the frequency domain. But in reality, we are experiencing temperature varying condition. Under the temperature varying condition, we can detect real damage into the steel truss member. Actually, this is the schematic model of Seunghee bridge, which was the collapsed member of Seunghee bridge in 1994, Seoul, Korea. So even under temperature varying condition, by using effective frequency shift, which is a kind of temperature compensation technique, we can detect crack damage and its growth, as you can see here, even under temperature varying condition. This is for guide wave based damage detection using same steel truss member. As you can see here, we can wavelet transform using time domain data. As you can see here, we can monitor crack growth by using wavelet coefficient from the wavelet guide wave data in a time domain. Okay, also to classify different kind of damage classes, we can embed pattern recognition technique. In this example, I used support vector machine, which is a kind of very similar to neural network technique. But we can train the support vector machine and embed this machine to classify different kind of damage classes. In this case, we classified different loosen bolt cases, as you can see here. So sometimes we need to monitor the damage, and we need to also classify different kind of damage classes. In this case, we can use this kind of pattern recognition techniques. Okay, now what I want to show you is a reference-free SHM using transfer impedance technique. Actually, I'm working with Dr. Hunson at KAIST to do this technique. In traditional SHM or damage detection technique, we compare between baseline data and concurrent data, which is potentially in a damaged state. But actually, this kind of pattern comparison approach is too vulnerable to other environmental effects, such as temperature effect. So sometimes this kind of pattern comparison approach provide us with false alarm damage indicator. So to solve this problem, we need to develop reference-free SHM technique, which is we can detect structural damage without any prior information. So as you can see here, we can put two pairs of PGT patch on both sides to the plate, as you can see here. Then we can use mode decomposition, as you can see in this equation. Then we can classify two classes. Class A, which contains both mode conversions. The other one, Class B, which contains only one mode conversion. By using this simple criteria, we can detect structural damage without any prior information. So we call it reference-free SHM. Like that. Okay, this is another approach, which is sensor self-diagnosis. Actually, in reality, the weakest part of sensor structure system is sensor part, not a structure part. So sometimes we need to check sensor installation status. We need to check whether sensors are working well or not. So we can monitor the slope of imaginary part of electrical admittance measured at the PGT sensor. We can tell PGT sensor breakage or debonding condition. Actually, this work from a collaboration with Dr. Gueva at Los Alamos National Laboratory. So this is a very important issue because sometimes sensor is broken or debonding between PGT and structure occur. So we need to check sensor is working well or not before health monitoring implementation. Okay, nowadays we are developing a wireless sensor network-based SHM in a ubiquitous computing environment. These are three important factors: sensing technology and network system and intelligence functions. As for the sensing technology, optimal sensor systems such as RFID NDT sensors are distributed a lot of critical points of civil infrastructures. Then networking system is important. Structures, device engineers connected in a network for transmitting and receiving data obtained from the sensors. And finally, intelligence function. Based on the information fusion technology, we can tell structural damage, and we can classify different kind of structure damage classes based on automated and intelligent systems. So why don't you imagine a lot of USN system distribute on critical members on bridge structures. This is the initial prototype of wireless impedance sensor node developed by Los Alamos National Laboratory. You can see here microprocessor and RF radio telemetry, and this is the impedance measuring chip device. So by integrating three items, we can devise one sensor board for structural health monitoring technique. This is another example which is combining two techniques, impedance plus wave propagation technique, which was developed by Dr. Danny Mann at Virginia Tech. In this context, I developed wireless impedance sensor nodes that consist of self-sensing actuator, signal conditioning algorithm and computing on one microcontroller, and also energy harvesting circuit and RF telemetry. So all the functions can be done on one chipset, as you can see here. So this is a final prototype that has all the function, as you can see here. So we can employ this kind of prototype into critical member of bridge structures to monitor health condition in real time. Okay, this is one package including this sensor prototype. This is a specification of this sensor node. We can get impedance data in a range of frequency range of 1 to 100 kilohertz, and it it is capable of temperature range minus 40 degree to 125 Celsius degree. And it has 2.4 gigahertz Zigbee RF transmitter. The RF range is 40 meter. Actually, it's not far from sensor location, so we need to extend the data transmission range. And also, we can supply power of 5 volt to 9 volt into the sensor node. Okay, actually in conventional technique, we are using very expensive analyzer, but our sensor node costs only $200. So we can save the money to employ this SHM system, but the performance is very similar. They show much the same trend and same peak frequencies, but different magnitude scale. But magnitude scale is not important. Just peak frequency information is important in our SHM applications. Okay, this is the our software using MATLAB for impedance node. We can monitor battery of sensor node as well. Actually, battery monitoring is a very important issue as well, because wireless sensor we cannot supply power continuously without wiring system. So how much battery the sensor node has is very important to be monitored in real applications. Okay, by using this sensor node, we can detect loosening bolt damage into joint member system. But in here, we have to save energy consumption of sensor node, so we can embed PCA data compression algorithm. PCA means principal component analysis. As you can see here, this is a kind of eigenvalue analysis, or we need to analyze only essential information. This algorithm provides us saving power consumption and only essential analyzing only essential information throughout denoising effect. As you can see here, we don't need to transmit all the data. We need just transmit essential information after PCA data compression. So we can use this algorithm our sensor node. Okay, this is a little video clip for loose bolt damage detection. I hope this is working, but okay. Let me use video clip directly. This one. Not working? Oh, sorry. Okay, this is piezoelectric sensors, and this is channel number 1 for left figure, and this is channel number 2 for right figure. Oh, some problem. Anyhow, currently normal condition for left sensor and right sensor as well. Normal condition, as you can see here. I loosened the bolt here, then damaged condition. This is real-time alarming. Then I again retighten bolt to the original state. Then PGT sensor integrate structure. Then we can see normal condition. Yeah, it should be normal condition. Yeah, you see? Okay. Anyhow, we can monitor the loosen bolt condition of joint member by using this technique in real time. Okay, I'm going back to my original slide here. Oops, sorry about it. Okay, again, this is another example using steel truss bridge member, which caused the collapse of Seunghee Bridge in 1994 in Korea. Actually, a 40 crack occurred on the welded zone section of steel truss member. To detect this kind of 40 crack in real time, we can put piezoelectric sensors, as you can see here. So from the experimental result, we can see clearly identify damage cases, even under temperature variation. Actually, this is too small temperature variation, not real case, but this is just laboratory test. And yeah, we can see the damage detection capability using this wireless sensor node.
What was the cycles? What was the nature of the cycle which induced fatigue? Is it thermal, or is it like basically stress amplitude?
You mean fatigue?
Yeah. What induced the fatigue? Is this a thermal cycle, or is this purely a loading cycle?
Good question. Actually, this experimental study doesn't use any real fatigue crack. For this experiment, we just put artificially cut. Okay. Yeah. That's a good question. Okay, this is another example to detect loose bolt detection at building structures. You can see here steel columns and concrete block. There are 4 bolts here. So by using PGT sensors and sensor node, we can see here detect loose bolt condition. Also, this is also artificial loose bolt, not real loose bolt.
And what about corrosion effect?
Not corrosion.
You could lose
Yeah.
due to corrosion, the tension in the bolt.
Right. So I need to think how to simulate real damage for losing bolt condition. Maybe we can induce corrosion damage or something into the bolt joint member, as you told. Okay, this is for real bridge cases. This is one bridge in Korea, real bridge. We employ sensor node here. Also, we check the temperature using thermocoupler. We attach PGT sensor here to monitor bolt loose bolt condition of jointed member. As you can see here, we can see loose bolt condition, and also we can see cut damage here.
How come after you retighten for number 1, it doesn't go back up to where it's supposed to be?
This one?
Yeah.
Yeah, we lose a bolt first, then we retight
But it
again.
doesn't go back up to the previous stage before you lose the bolt.
Yeah, this is.
This thing is not the same as the first one.
Yeah, actually, yeah, maybe internally different condition, right?
So
Yeah,
you got this one time.
yeah. So we check the repeatability. You see here? Okay. Yeah. Again, this is that real damage. I need to think how to simulate real damage for this example. Okay. Just I check the feasibility of this technique in real bridge structures. Good question. Thank you. Okay. Another one is I want to use mobile telecommunication technology for health monitoring system. So nowadays, many people use smartphone, right? So this is 3.5G generation technology. What we call is HSDPA, high-speed downlink packet access. This is 4th generation mobile telecommunication technology already developed, but anyhow, I used 3.5 generation technology. As you can see here, HSDPA 3.5 generation technology has better performance as compared with other WCDMA or other CDMA technology in terms of data transfer rate. So by using this technology, we can transmit and receive data even under we use high frequency data at the short period. So I implemented this mobile technology into rear bridge system. We can monitor real-time traffic condition, and we are using piezoelectric sensors and fiber optic sensors and accelerometer and temperature sensors. So this is one example. We are working in Korea. This is a bridge test bed project for US-Korea joint research sponsored by NSF COSF since 2007. Actually, my PhD advisor, Professor Yoon at KAIST, developed this project. He has been working on this project with Professor Lynch and Professor Wang in US. So we implemented those sensors in 3 kinds of bridges by using mobile telecommunication technology. Okay, I'm going to show you another video clip here. I'm sure. Still not working. What kind of program? Oh. Hopefully. No. Sorry about it. Okay. Here we go. Their measurement system installed into Geumdang bridge here. We can implement data. This mobile telecommunication system for data acquisition and archiving. So we can see real-time data from including accelerometer, strain data from fiber optic sensors, impedance and wave data from piezoelectric sensors by using our mobile phone, our smartphone. So by using our smartphone, we can see real-time data into the bridge. So we can check what problem with it, or we can check what condition with it, real bridge structure. Okay. Now, those systems are implemented into Geumdang Bridge in Korea. So if you come to Korea, I'm gonna guide you see monitoring system in real bridge. Okay. I'm gonna pass. Okay, this is second item, which is energy harvesting. As I told you before, when we use wireless sensor network, we need to supply power effectively. We need to check how much battery we need. We need to check how much battery does the wireless sensor has. So we need to improve power management, and we need to develop energy harvesting module inside a wireless sensor node. As you can see here, this is very interesting figure. We can harvest energy from the some vibration. Actually, whenever animal breeding is breeding, it induces some vibration. So by using the vibration, we can harvest energy from the animal. So wireless technology allows electronics and sensors to be placed in remote locations. Continuous advance in low power electronics and MEMS technology is required. Powering wireless sensors for years requires new advance in energy sources. So by using some ambient vibration effect, we can harvest energy. From this idea.
What happened when the bear hibernate?
Right. From this idea, we are thinking about piezoelectric vibration. So as you can see here, there are a lot of energy harvesting issues, but solar, thermoelectric, and microgenerator, they have also limitation. So we want to develop hybrid energy harvesting modules. So by using vibration, we can harvest energy from the piezoelectric material, as you can see here. This is also, we can understand, what happened? Sorry about it. This piezoelectric-based energy harvesting, also we can understand from this equation. Actually, harvesting vibration using piezoelectric effect can be configured in a number of ways. Simplest way is layered onto a structure, and another way is cantilevered of a vibrating mounting point with thin mass, as you can see here. So we can put PGT sensor as a biomorph system or as a unimorph system, as you can see here. So we can compare different configuration using PGT installation. Here, we can compare between MFC and PGT sensors for performance comparison for power generation. As you can see here, we put MFC sensor or PGT sensor onto the blade. Then on one side, we can excite some vibration by using shaker system, as you can see here, and we can check how much voltage we can get from the vibration by using oscilloscope. Actually, we excited a shaker by using sinusoidal waveform with 4G acceleration and 0 to 300 Hz frequency range. As you can see here, the result, PGT type 1 is the best way to harvest energy from the vibration. Even though MFC has high voltage capacity, but as you can see here, it has low power capacity. So we concluded PGT type 1 is the best energy harvester by showing high power capacity. This is the energy harvester for piezoelectric energy harvester. Energy harvester module for piezoelectric energy harvester. As you can see here, oops, sorry. A lot of files. Okay. It consists of PGT plug, rectifier, reset IC, and 3.7 voltage battery, and time delay circuit, and sensor node plug. Actually, time delay circuit is very important function. We can see here WSN, wireless sensor node operation, for data measurement and transmission. So we can monitor the power required for sensor node in real time, as you can see here. Okay, this is concluding remark combining structuralized monitoring and energy harvesting to provide place and forget ubiquitous monitoring system. We can employ this kind of onboard chip system to monitor health condition of host structure, and also by on the use of this sensor node, we can harvest energy from the structure vibration, as you can see here. SHM can be placed on a chip to construct a self-contained wireless monitoring system that broadcasts faulty information. Harvesting energy may not be enough. One must also address the issue of minimizing energy use, storage, duty cycle, ambient energy sources, or matter. Okay. From now on, I'm gonna introduce my future research plan. Actually, I want to develop automated inspection robot and motion control system can be applied for bridge structure, as you can see here. What you see here is the Roomba. Roomba is robot cleaner. We can use Roomba robot system at home, unmanned autonomous vacuum cleaner robot. As you can see here, Roomba can make clean even hard to reach places, vacuum hard to reach place by manually itself. Also, whenever its batteries ran out, Roomba can automatically return to its home base to dock and recharge its battery, as you can see here.
It only works for square rooms.
Mm-hmm.
If you have rooms which are complicated, it never comes back. It gets lost.
Right, right.
I want you to know that.
Yeah, right. Anyhow, by using this technology, we can employ automated inspection robot and motion control system without any powering system, you know. So our idea is we can use unmanned inspection robot with having SHM and energy harvesting sensor board. So we can use optic-based wireless power data transmission for active sensing SHM technique. Also, we like this. This is another plan is to develop UAV remote health monitoring system by using HSDPA telecommunication technology I already mentioned before. So we can put PGT sensors and FPG sensors onto the plane wing to check the health condition of plane wing, as you can see here, and we can communicate sensor data by using this HSDPA technology. Actually, in Korea nowadays, there are a lot of collaboration opportunities. We call it VC 10 project, Value Creation 10 project by Korean government. Here is the list. Ubiquitous Eco City, Urban Generation, Super High-Rise Buildings, GIS, smart highway, long span bridge, high speed rail, and others. So Korean government invested a very big fund for our for many research team, including my university. So by collaboration with other engineering domain, we are trying to develop UCT technology, IT convergence, and bio-inspired smart sense technologies. Okay, before I close my presentation, I want to briefly introduce about my university and my department. Actually, Seunghee University is the oldest private university in Korea, more than 600 years. Generally, our university is top 5 ranking university in Korea. First one is Seoul National University and KAIST, two universities similar rank, and then Korea, Yonsei, and Seunghee University. So Seunghee University is the 3rd private university in Korea because KAIST and Seoul National University is national university. So very high-ranking university. Also, the owner of Seunghee University is Samsung company. So we got big fund from Samsung. Also, I got my salary from Samsung company. So I'm trying to develop many new idea and many new project to get big fund from Samsung company. What happened here?
No power.
No power? New idea and new department. So in this context, last year, new department, the name is Department of UCT Design Engineering, initiated as Seunghee University. UCT means Ubiquitous City. So we now master and doctoral students are financially supported from government, and there are 4 universities in Korea: KAIST, Yonsei, Kongguk, and Seunghee University. So we have 4 tracks in the department: planner, infrastructure, and construction manager, and first facility engineer to develop ubiquitous cities. Okay, so our department want to contribute following issues: collaboration with the national R&D project, industrial academic cooperation, international activities, multidisciplinary research and education, and public advertisement. Okay. Final vision of our department is to develop intelligent ubiquitous cities based on smart structures, ubiquitous sense technology, and information technologies. Okay, that's it. Finally, I would like to acknowledge the support by Professor Jung Bang-yoon at KAIST, Professor Danny Man at Virginia Tech, and Hun Son at KAIST, and Gue Bak, and Dr. Chuck Farah at Los Alamos National Laboratory. Okay, thank you very much. Any questions?
No question. Okay, so we maybe have some question from the audience. Don't ask question about the bear. I have already asked this one, but we may have other questions. Yes.
Was your online damage detection based on a statistical pattern recognition, or you had trained your system before?
We can use both approach. Yeah, sometimes we need pattern recognition technique because we need to establish optimal threshold to tell health condition and damaged condition, right? We need to establish threshold, optimal threshold. To do this, we can use statistical pattern recognition technique. But sometimes we don't need to we don't need any threshold. You know, at that case, we don't need to use pattern recognition technique. So we can do both approach for structuralized monitoring, whatever you want.
And in your system, the MATLAB program was statistical, or was your system was trained before?
What do you mean?
the one that you were losing the bulb,
Yep.
and we could identify the damage.
Yeah.
Was that based on a statistical analysis? Or
Yeah.
your system was trained
Okay.
before?
To tell the health condition and damage condition, we need to threshold, right? So to obtain the optimal threshold, I have to train the data, statistical method, right? Okay.
How did you do temperature control? Because I noticed in the data you in some of the slides you had said that some of the data was corrected for temperature. How did you do that?
Damage control?
To like when you're doing identification, were you controlling for variability in the temperature? So like stiffness changes due to temperature. Did you correct for that?
That's why we need to develop, we need to employ temperature compensation technique, right?
Yeah.
Yeah.
What technique did you use?
Yeah. Okay. Here. Okay, this is the impedance data in a frequency domain. Impedance means a kind of FRF, frequency response function. So these peaks present resonant frequencies in structure vibration. So as you can see here, the temperature changes, those peaks just shift parallel with a parallel shift. But if damage occurs in a structure, maybe some pattern should be changed.
Okay.
You know, so we can use effective frequency shift based on correlation coefficient, because if some pattern changes, correlation also changes, right? But pattern same, correlation same, right?
Okay.
So we just check the pattern of impedance data under temperature variation. Okay.
You showed a live monitoring of the battery of the wireless sensor, right? Have you noticed any measurement in accuracy when the battery starts getting really low?
No,
Okay.
that should be a good question.
Yeah, I'm
Yeah.
just wondering if
Yeah,
there's
yeah.
a special battery.
So our sensor node has,
Yeah, we saw that. That's why I wanted to ask.
yeah, our sensor node has the function for battery monitoring right now,
Yeah.
but
The battery never gets really low.
yeah.
I have a questions about fatigue. Fatigue is usually a very slow evolving phenomenon. You have fatigue, we characterize fatigue with a diagram we call the SN diagram, which usually relates the number of cycles with the amplitude of the cyclic stress. Typically fatigue for metals like a cast iron or metal will go into the 10 to power 6 million. So it's evolving gradually. The fatigue will develop cracks in a very, very slow rate. So we're dealing with something at some point which is going to evolve in a large crack, which will propagate suddenly. So we are dealing with something slow, and suddenly we have an acceleration, quick, which trigger a rupture, usually a brittle rupture. So how can your system capture something which is evolving so slowly?
Always tough question. Right, very theoretically, right. Yeah. Now I didn't focus on, real fatigue damage, as I told you already. So maybe we need to think how to simulate real damage, and I have to check your question later. Very good question. This is only for artificial damage, just cut, just artificial loose bolt. But corrosion and fatigue process very slow, right?
Very slow, and I'm
So,
concerned that
yeah.
your systems may actually fatigue faster than the actual members that you're trying to monitor.
Yeah.
And so we have to look at how steady, how consistent, how permanent your systems are compared to the structure you're monitoring.
But anyhow, this technique aims to continuous long-term monitoring.
Yeah.
So maybe we need to use statistical analyzing data analyzing algorithm. Yeah. If we can use statistical analyzing algorithm, maybe it can be possible, I think. Let me check. Thank you for your comment.
Okay, so if we have no more questions, I would like to close the seminar, but before we close, we would like to thank the speaker. Thank you.
Thank you so much.